Hello, my name is Sarvesh Mangala and I have to give you a hands-on session in CASA, which is a Common Astronomy Software Application. I hope you have already installed this in your Linux machine or Mac OS if you are using it. So if you have difficulty in installing the software, I'm here to give you like a brief thing to how to install it. So I just downloaded this file, this file. Okay. When you click on it, it will automatically start the installation. So I have already installed, so I am cancelling it right now. So I moved the folder to in my home directory. As you can see here. So this CASA release 5.7, you can download it from here. So how to untar it first? So trxvzf and give the name of the file to CASA. It will automatically untar the file. Just wait for it. Okay. It took less than 1 minute or 30 seconds. So you can see there is a folder by the same name. So you have to go into the folder. I was just checking it is recording or not. Sorry. CD pin. You can see there is a CASA file here. So you need to export this path into bash RC. So I'll just pwd to know the path and just gedit go into bash RC. This is how you export the path. Export path. Give the path name, right? This $sign path. Yes, and just save the file. Do not ever delete this file. Okay. If you do, your Linux machine will get corrupted and you have to install it again or call a technician or something. So just bash. The source means execute the file. Something like execute. So if you run CASA now, CA, and it will show you CASA. Here CASA. So it's just like Windows with all software. So we go back to the data. So I am doing the data. This 3.1 GB data, I have splitted the data into small bin 328 MB. So I'll use this link to install, which I have already given you the link also. So you must install. So here is this file link. Same thing, you have to untar it. tar xvzf and 3c. So there is a MS file name. MS is a visibility file name. I will tell you about this. So first thing you want to know about the CASA, that it reduces the radio data to make you images of the sky. So if we go step by step, then we will first inspect the data. We'll do the flagging. Flagging is something that you delete the RFI. So RFIs are radio frequency interferences that are the interferences in your data. So it's a bad data. So you have to flag your bad data and keep your good data to make an image. So how to make an image? We'll do the calibration. Okay, why do we do calibration? So calibration is something that you do because your interferometer or a telescope or whatever camera you are using, So you have to record the exact picture that you are watching. So interferometer are connected with the voltage supply, and they just record the voltage. So they record amplitude and phase. So it basically records the electric field between, if there are two antennas, so you do the correlation between the two antennas and record the data. So it's a record amplitude and phase. So why do you calibrate it? Calibration can be done because of the certain that you remove certain errors, like in phase you see a phase jump, or there is a spread in amplitude, in the time or frequency regime, right? So and then we'll do make an image and do the self calibration. Self calibration is that you do the calibration on the image to get the better image. Okay. So if there is any, so the first thing I told you about, just don't panic. Okay, the panic is the worst thing that you can do. So don't panic, it's a very easy thing to do. So what you see from in the electromagnetic spectrum, so at what regime you are observing. In gamma you use a satellite, in X-ray you use a satellite. Why do you use a satellite? Why can't we just observe it from the ground? Because of the atmosphere opacity. So there are certain ranges in the electromagnetic spectrum that you can see from the ground, and there are things that you can't see from the ground. So you have to go to space. So there are space telescopes, right? In optical there is a window, small window, and in radio. And as you go into the low frequency or high wavelength, there is a ionosphere cutoff. So ionosphere cutoff is around 10 megahertz. So before low frequency than 10 megahertz you can't see, because it's the ionosphere it's a glass slab, right? Ionosphere is like a glass slab, and there is one point the ray can't penetrate. So it's like that. So you need radio data, so you can observe from the earth. So this is the type of radio telescopes are there. So GMRT is using these telescopes, 30 antennas like this. So as you have seen from the diffraction theory, you already know what is if there is a slit, right? So what is the resolution of the slit? So the resolution of the slit, the frequency that you are observing, and the width of the slit, right? So it's lambda by d. So if there is only one antenna, so how much d can you make, right? So you know, if you can't make a 5 kilometer dishes, right? So you can make a 300 meter maximum, 400 meter, 1 kilometer is also a big one. So this is the resolution that you depend on. So better the d, bigger the d, better the resolution. So but we can't make, there is a limitation for d. You can't make so many big dishes. There's so many problems. Money is one. So what we do is use a double slit, right? So if you use a double slit, you can just change the length between these correlators, these antennas, and get the better resolution. So when you point both of the antennas towards the source, there is a geometric delay, right? Because the signal is not reaching both the antenna at the same point. That is why there is a geometric delay which you have to correct it, right? So we can use many dishes, right? So it's a double slit experiment with not two slits. You can have multiple slits. So if you do the correlation between the pair of antenna with the electric field, you get a visibility. So visibility is this, and it corresponds to the Fourier component of the sky brightness. So you see the sky, and the Fourier component you will get, which we call as visibility, which also known as mutual coherence function. So when you see here, this is XY plane, so the antennas are in the XY coordinate system, and this plane, the parallel plane between the rays is known as UV plane. So you can know much more about it. I'll tell you about one theorem that you can learn from that. So using the earth rotation, so if there was a single dish, then you see a point and the point will be close. So you need bigger UV coverage. So bigger UV coverage. So if this is filled, then you get a one telescope, right? You get the full big one telescope of how much. So here you can see here in the maximum baseline for short VLA in D configuration, you have the maximum baselines of 1 kilometer. So you get this small antenna of 25 meter each dish size, and when you do a UV coverage, in the UV coverage you will get 1 kilometer. So 30 antenna of 25 meter will give you, if this UV coverage is filled, so you will get antenna, you will get a telescope of 1 kilometer. Okay, that is pretty amazing. So you just exploit your physics to get the data and do the science. So this is a sampling in UV coverage. When you do the Fourier transform, you get the sky brightness. The first thing that you do is get a PSF. PSF is what? Response of the system to a point source. So it's a point spread function. So I told you about the cleaning part, and so before, to make an image, so this is the dirty image. You do deconvolution and get a better clean image, right? So this is what the source look like now. It is look like this. You can't even like point out, is there any sources here? No, you can't see because it's all noisy. But here you can see there is a source here, there is a source here, with the bright one. So now there is a problem that are coming that we face, and that's why we need calibration. So when the atmosphere is one problem, ionosphere is another, and there are many pointing errors with the pairs of antenna, and thermal noise, antenna noise, RFI, your mobile phone's frequency, everything you have to calibrate and like flag the bad data and to do the science. So the data that we are using today, so I made a plot of UV coverages with the flux density 3C286, which we will call our flux calibrator. So this target source, the UV coverage of these calibrators, the field that we have observed. Okay, now let's go to the data. So let's start CASA here. When you start CASA, you will get the CASA logger also. So you can see what you are doing and how it is performing. You can see here. So if I do any task here, like anything, list ops. Let's open the CASA tutorial also that you're gonna follow. I'm gonna follow to teach you. So this is the link in the slides also. There is a link for the CASA tutorial. So what we know about how we inspect the data, I told you you should know what the data that you are working on. So let's check what is the data. So it's a data of a supernova remnant. So there is a simple task that you can do is list ops. So INP to see the give the task name, and you can see what input parameters that you can give. So INP list ops. So you can give your visibility file name first, which was 3C. I just pressed 3 and I did the space things to get the file name if there is a file name in that folder. Okay. if I put a wrong file name, let's say there is no file name by this name, so if I do np again, it will come out to be in red. Okay, so it says there is no file name that is here. So if you put something wrong parameter that it shouldn't be there, so you can get this. So if I put visibility again, the same correct parameter, so INP again, so it come out to be blue, which is good. Select data true, and this and go is to run, execute the task, right? So go, and in the CASA logger you will see here what list jobs have done. So you can see here is begin task list job, and the task was run, and you can see what the data is. Okay, so what things you should like see in the data is there are number of scans. So there are 102 scans. I removed some scan during the splitting the data to make this data size smaller, that you can all download, but you can also download the full data set of 3.1 GB and do the calibration and all. So here you can see is J1331 plus 3030. This is a flux calibrator, and J1822 minus 0938 is a phase calibrator. So I told you about the calibration, right? So what we do, why can't we see only the source, why the target, only the target we can watch, and we don't need calibrators. Why do we need calibrator? So there are two calibrators that you should know about, you should do, is flux calibration and phase calibration. So flux is the amplitude gain calibration that you want to do, so it's to correct the amplitude, okay, and phase calibrator is to do correct the phase. Why? So we for the flux calibrator you should take a point source, because if you do take a result source, then in the frequency you will see some more structures that you have to be pointed out, you have to correct for those also. So just take a point source, which would be bright source, and you should know from the calibrator manual, or people have thorough research and precisely known the flux density of the source to the amplitude calibration, to do the amplitude thing. The phase calibration, so amplitude in the sky, that's your text, your screen is the sky right there, and at this you see a binocular, right? So this is your target. So the target is moving, right? So you can have a flux source here, which is also moving, but when you see the patch of the sky, the flux calibrator should not be into the patch of sky, because I told you that the flux calibrator should be a bright source, right? So if it's brighter than target, then there is a problem. So you will only see your calibrator, you can't see your target, because target is the people do the target when in micro Jansky, and the flux calibrator are in Jansky, like 32 Jansky, 52 Jansky, depend on the frequency that you are observing, but yes, they are bright sources. And the phase calibrator, you have to do the phase calibration with time. So the ionosphere is changing, the atmosphere is changing, so you need calibration with respected time. So the phase calibrator should be near to the target, okay, like here, if this is the target, the phase and this is the patch of sky that you are observing, so phase calibrator should be near. So here you can see the array deck of all the fields you are observing. So you can see the array deck of the flux calibrator, which is very far from the target and the phase calibrator. So this is the target 3C391, and J1822 minus 0938 is your phase calibrator, which is observed like again and again, right? Again and again. Target, flux calibrator, phase calibrator, target, phase calibrator, target, phase, target, phase, target, phase, target. Also, people do sometimes take the flux calibrator in between, in last or in starting also, and the phase calibrator, target, phase calibrator. So this is how you should take the data. So what should we check? how do we inspect the data? So the first thing you check is the central frequency. So this is 4.5 gigahertz data. What is the bandwidth of the data? So the bandwidth is total bandwidth is given here 128 megahertz. And what is the channel width? How many channels are there? You can see how many number of antennas are present. You see there is a name of the antenna EA0102 to 28, but there are some antennas which are missing. So let's see, there is antenna EA10 is missing, right? So and there is a given ID in this, right, 0 to 25. So this you can see as a serial number, but EA16 is not same as 16. You should you should make sure that you don't put the wrong antenna when you do something with the antenna, right? So, and there are the two polarization with the data, this RR and LL polarization. You can see what is the integration time of the data. Integration time is the like shutter thing, okay? So when you put a camera, you take the data every 10 seconds. So this is, you can see the time. Is what I'm missing. You can see the array, the latitude, longitude of all the antennas. So let's go further. Okay. Let's go back to the manual. So this is the task list of. You also can give the task like this also. Again I am running it. You can see here, if I run, what happened to this CASA log, right? Okay, sorry, manual is it ran too fast. I think you didn't see it. Let's make it default and you will see now is it running or not. Right, so setting values to default. So if I do run it again, it stops. You see, it ran very fast. You can also see the data. You haven't seen the data, right? People don't see in radio astronomy. People can't see the data. So it's like this: tv.open and file name. So its file name should become this. And tv.browse the data. So you can see what is the data is about. So there are UVW points. There is a flag column. So there are two polarization and 64 channels. This is the time. This is the data that you want. So data in both. So this is X and this is Y. It should be something like that. So you get an amplitude by squaring it, both of them, and just take under root, and you get the phase by tan inverse this by this. So 64 channel, 2 polarization. You can see the antenna number, so 0, 1, 0, 2, because there are like how many antennas are there? There are 2, 6, I think. You can go back to list of and check, right? So from 0 it's starting to 25, so there are 26 antennas. So how many baselines are there? So let me check here also. It's a formula for NC2. So you can check. If there are two antennas, there's only one baseline. So baseline is the when you do the correlation. So how many correlation can you have? So 2 antennas is one baseline. So 3 antenna is it's like taking point A, B, and C. So AB is one baseline, AC is one baseline, and BC is one baseline. So there are 3 baseline. So if we do four antennas, so how many baselines are there? Like 6 baselines. So it's 4C2, which is 4 multiplied by 3 divided by 2. Okay, so NC2, there are 26 antennas. 26 multiplied by 25 divided by 2. So there are 325 baselines. So at each times 10, you are getting 325 baseline, 1 and 24, and how much? 64 channels are there, right? 2 polarizations. So if you multiply both of them, multiply at each times 10 and multiply by the number of hours that you have taken the time, so you get the whole number of points that you get this, right? 650. It's a scan of like 20 seconds, so it's only 325 multiplied by 2 polarization and all, so you get the how many rows are there, right? Yeah, 20-second. You see there is a 20-second, only 20-second the source was pointing, so you don't get much information from this, so you should flag this scan because it's a bad scan to put. So let's go back to the manual and see what is there. So you can, the 3.1 GB data set has these many scans, so I just there are 7 pointings. So what are the pointings? Okay, so if you see again, consider your screen as a sky, and you want to watch this whole screen, but your the patch you can see at one time is like, let's say this, right? Okay, but you want to see the whole screen. How will you see it? So you will first point your antenna telescope here, then observe it for 10 minutes or so, and then point here, and it's just like divide the patch of the sky into in this you they have divided the patch of the sky in 7, and you see there are 7 patches, and when you merge them, so is a mosaic thing, so you merge to get the whole screen or whole sky, right? So there you can see there is a field ID which is 0, 1, and the target scans, and there is a polarization calibrator also. So there are 2. I have just taken 2 polarization, RR and LR. People also do RL and LR, which is like a kind of difficult, and GMRT doesn't have the. I think they have. I don't know, but polarization calibration is very it is difficult task to do, and I don't know how to do it. I haven't tried and yet, and this you have to like follow another tutorial to do that. So we will not do that today. So these are the XYZ, the scans, and now let's plot our antenna pattern. Okay, so it's plot ends. So again we do that INT plot ends. Okay, let's give the visibility thing again. INT, you can see here, flag backup, show GUI true, title for the plot if you want to give a title, fig file, you can save the antenna pattern also. Let's save this fig file, antenna, antenna.png, let's say INP again. देखो, visibility I put wrong. Okay, so number of points plotted is 26. So you can see each antenna name also the corresponding thing A0. You can see they are not like in sequence 0, 1, 2, 3. So don't confuse about the when you see the list of, you should plot this and should know where are your antenna lies. So you can see there is 600 to 600, so like 500 500, so the maximum baseline. So maximum baseline is, you can see here can be a maximum baseline, this can be a maximum baseline of this, so it's around 1 kilometer that they have. So this is the antenna plot for VLA in D configuration. So IA configuration have maximum baseline of 50 kilometer also. Okay, so you can just cross it here, and you can see there is a new file generated, this antenna.png. Okay, so in the folder, go to the folder if you want to see, and there is a really a file, or I'm just joking it about. So you can see here. Right? Now we want to remove the bad data. Right? So I already told that the scan 1 was less than 1 minute, right? So that was a bad scan. So what should you do? Now let's say I will do INP flag data. The visibility get automatically done. If you do like this, it will not. If I just copy it here and just put and try here and paste, it will get run, but if you do the INP, it will not come. So it's better for the beginners to. I'm just gonna charge my laptop. It's close. Sorry. It's good to visualize your data. So see what the task you are running. Maybe you run something bad and just delete the whole data set. Okay. So visibility is this, mode is manual that you are doing it. There is no another algorithm who is doing it, you are doing it. So do it manual mode, right? So what scan was bad, right? You give the scan name. As you can see, there are strings. So if I do scan 1, it will automatically give me the bad thing. It's in red, so I've given him the wrong input. That should be in string, right? Action is applied. Yeah. I'll tell you more about it as we go on. You can have a flag backup. Is like maybe you have done something wrong, right? You shouldn't have deleted the data. That's why you are taking a flag backup. So if I do ls, there's only one. Now I'm running it, and you will see what will happen. So INP again and flag data, just to see the parameters that you have given to. So it's better to check last, because if you do it, then you have to go back and you correct your mistake, right? So to speak to here you can see it's flagging the whole data, your scan 1, right? So it's flagging, it will take time. Also you can check that as I have done flag backup to be true, is create a new backup flag file called flag data 1. So you can you can also restore it if you have done something wrong by doing another task, right? So I have shit, there's something wrong that I have done. Maybe it will not flag it. I don't think it will, because I remember I gave tb.open file name, tb.browse, but I didn't close it. Now it ran because he didn't have the right permission then. You can also check if it's flagged or not, right? So how do we check it? So it's INP again will do, and in mode you see go and take summary on INP. Action calculate. So for scan 1 it's saying ki all antennas are flagged. Okay. Now let's take scan to be still. So it will take all the scans. Okay. So let's go again. So it's checking in every scan, and it's checking in every scan, every field ID, and it's giving this. So here you can see the scan 1 is totally flagged, and you can see in each antenna only 0.351% of data is flagged. Okay. Around this. So scan 1 is of flux calibrator, so only you can see in the field ID that only flux calibrator 1 scan was flagged, which also is of 2% only. It's better to delete all the bad data. Okay. It's a good practice to remove all the bad data that you can find to make a better image of the sky. So you just minimize it. So there is a when the observatory take data, so there are certain certain things that can go wrong with the antenna, right? Maybe there's antenna that was not working at that time. GMRT antennas, in my data set there are 3 antennas which are not working at that moment when my data was getting taken. Okay. So the observer, the people who are there on site, make an observer log. Okay. So if there is certain antenna which is not working at certain frequency, or there is a wind condition for that antenna, or that antenna is bad, something is going on, their repairing is going on maybe, so they can't just stop the facility for you, for the people, for the science community, right? So that antenna is not working, so they make an observer log. Okay. So they put something, so it's manually been built. So the observer log, you can download somewhere in the link. They have given the link to check. You can go there and put the date of your date of the observation, and you can get the observer log, right? So in the observer log, the observer has already put that these both antenna EA13 and EA15 were not working. So what you should do is flag the data. So right, so we'll do it again. So if you were get, let's say, default flag data, okay. INP, it's blank, right? So if I do tget flag data, what will it do? It again show the thing that I last ran. To get all the parameters back, you just have to go tget flag data. Okay. Also, I just forgot, if there is help that you want with certain parameters, so it's like help flag data. So it will show you how the flag data is working, right? So there are how many modes are there. So I just told you about the manual mode, right? And you get a summary. There are many modes like list, manual, clip, quack, shadow, elevation, TF crop, RF, R flag, okay, extend mode. I'll tell you some of it at least, and you can see what are the different parameters do. Can the links of the papers also. What is the allowed value? So allowed value is like this. that you can't say, you don't want. There are some example also given, I think in the last maybe. Okay, in this they haven't given it. So if you want to go back, just press Q. Q is for quit. Okay. So we'll do it again. We'll flag these both antennas. So let's see, by deleting, I told you about 325 baseline, right? So if I delete two antenna, how many baseline will be left? So it's, let's check. So 26 antennas minus 2 will be 24 antennas. 24 multiplied by 23 divided by 2, right? So 276. We have before we have 325 minus 276. There's 49 baseline is gone, right? So let's check in percentage. So is 49 divided by 325. Oh, sorry. So this CASA runs in Python 2. Okay, so it doesn't understand if you. I have given both the parameters to be 49 and 325, which were both integer, right? So you should have given float. So it will say. So this multiply by 100. But 15% of my data will be being flagged. Okay. So let's do it. INP mode, I'm gonna change back again to manual, right? INP again, manual. Action will be now to apply. Okay. Antenna, which is EA15 and EA13. So 13 was first. Remember, you should give in serial order. It's better practice to do that. So these two antenna, and let's see what will happen when I go, right? Go and enter. So it's running it already flagged. It's last time in. So each let's check back again. Mode summary. Antenna INP. So I told you about, right? Around 15% from each scan is deleted, right? Antennas. So it's around 15%. Total flagged is around 15%. Right. Now let's go back to the slide. I want to show you one thing. So there are different antennas. Let's say there is a all pointing toward this. Okay. This small black thing, you can see. I think you can see. You can see. Okay, all pointing. So let's say it was first pointing here. Okay. So now all my antennas are moving toward this source. Okay. So maybe this antenna will come up first here and start observing, but this antenna or this, let's say there is an antenna right here also, okay? But this antenna will take some more time than this antenna to come back to its position. So let's say, so it's kind of a thing that you should know that maybe there's a time delay, right? So maybe it will take 10 seconds or 5 seconds, whatever it is. So it usually take 3 to 4 seconds to all point to all the antenna pointing in the same direction. Okay. So what I told you about in our data set, the integration time is 10 seconds, right? So I should delete my first line right? First line from every scan, because I told you that it point towards a calibrator, flux calibrator, then phase calibrator, then target, then phase, then target. So let's say the target is here and the phase calibrator is there, so all antennas are pointing toward taking one scan here and then again here. So it is changing, right? So every time is go back, change again, go back, change again, go back, change again, right? So in every scan there's one data set, like 3 to 5 second data set, that is to be flagged, which is kind of a thing that it can be a bad data or a good data. It can even do a good data, right? It can be, but it's usually general practice to remove the first 3 to 5 second of data, and in our data set is already the 10-second data set. That's why I'll delete my first line from every scan in the time region, right? So how do we do that? So we do that by using mode quack. So quack will quack the data. It's not like Donald Duck quack quack. So mode, let's go back to mode quack. Now I'll do the NP again, and these parameters are changing. Before it was minimum, maximum, something like that. Now in the summary mode, right? So if I change back to mode quack, we get certain new parameters that we can give. So quack interval is generally given in seconds, and it's not a string. It is a float. And second, from scan beginning or end. You can also delete from the end also. So quack mode I have given the flag mode to be quack mode is beginning. So you can give end also. Maybe the last point also is bad, but generally it is not. So let's go quack interval to be 10 seconds. Oh. INP, then quack, flag backup is true. I didn't tell you about LS. So there are flag versions, right? Before it was only one file. Now there is a file name point flag version. So this is a folder again. So you can check here also 3C3 one flag version. So when I flag, there is a folder that has been created inside. There is a backup, right? If you want to restore what you have done, maybe it's wrong, so you go back and do restore the thing and do it back again. So INP, I'm doing it. Go, and the CASA logo, you can see there is a running fast, that's why you can see the CASA logo is being generated at that time. So visibility, quack, and the flag dataset 3. It's LS again. LS you can see again. I'll show you. There's a new folder that has been created inside this flag version folder. Okay. There's a task or clear stat. If there is any lock that when I opened, right, before, so it made a lock to not to do anything with the data, so I can't. So just clear stat. You can see here again, clear beginning task clear stat and task clear task. Now let's visualize the data. You see numbers. I opened you table, right? So let's see the data for the first time. What is the data? How it look like, right? So there's a command called plot ms. So ms is visibility, right? Ms. So plot ms. Better to go for default first. INP. So there are two ways to do it. I can put visibility here again. Okay. And INP again. Check. So should we plot? So if I don't give anything, it's already been x-axis to be time and y-axis is amplitude, right? So if I go, let's check what happens. So if you do this plot MS on the whole data set of 3.1 GB, it will take time. Okay, so you should know how much RAM your laptop or computer or desktop, whatever you are using, holds. Okay, so you should know. So let's put only field 0. Okay, so field 0 was my flux calibrator. I got it again and it will run first. So this and this. So in the list of you can see again if you want. Let's go back to the first thing that we have done, right? So this field name, this flux calibrator. So there were three, and the first one we have deleted it. Only 2 were there, and again there was one in between, right? 1055, 1057. So it was around 2 minutes. 1055, around 1057. It doesn't show you the flag data that you have flagged. Okay, so only you can see the data that was unflagged. You haven't deleted it. Okay, so this is the amplitude spread, and so the spread of amplitude in each field is partially due to the difference in gain on each antenna and baseline. Okay, data calibration is done to just minimize this spread. Okay, so it will come, you will see there is a, now you can see what is the spread is 0.05 to 0.225 or 30. You can see 0 to 30, 0.0 to 0.3. So the calibration will much take care of this, right? And there are axes. So if I want to, let's do phase. Okay, now you will see something very like 180 to 180. So like phase is distributed, you can't see anything. So let's point it toward only one antenna. Okay, EA, let's say which antenna we want to point. Go back to CASA logger and see which antenna we want to see. Let's say EA 20. Okay, EA 20. Now you can see something, right? Iteration, let's do empty baseline. Another baseline. Okay, so you see there are some like this and some like this. So what is that you are missing? So it's like 8, right? So this scan was missing in this data, in this baseline. Okay, so if I point, let's say my scan number was 1, you have to go back to your back again and again. Okay, just to check things. So let's go to scan 2 only. Now you see. So there is a phase spread. Each baseline you can print. Let's go back and see amplitude. Okay. Yes. What you are seeing is there are 64 channels. Okay, you can also put into that. Let's go back and change the time into frequency or channel. let's see. So there are 64 channels, and now you see there's in between you get a good amplitude distribution, but at the end of the channels you get this like bad thing. So people usually delete the end channels and the starting channels also. In everything you will see there are like 1, 2, 3, 4, 5 channels here. 1, 2, 3, 4. And I already told that there are two polarization also. Okay, let's like colorize the polarization. Okay. So there is one polarization by one color, blue, and one is by green. I can't know for sure that you can see or know, but you can just give it here. I want to see only the RR polarization. Just plot, you will get RR only. Let's do the LL thing. You will get the LL. If you don't give, it will take both and colorize the thing. So go and just quit. Let's go back to this what they are doing. So for the sometimes people like if there is a huge data, right? So I'm running it again. Default plot ms and plot ms to run it again, or go whatever you want. So I browse, I can give parameters from here. Let's average it over 64 channels, and okay, this field I don't want to. Oh, I have to change the axis, right? It should be right. Let's colorize the field. Okay. Every field has its own color. So the black one is your flux calibrator, and the pink one is your phase calibrator, and orange is target. So the data missing was the 7 pointings that I was already telling you about. So it also come out in different colors. You can see here, right? So it's the black layer and each thing. And this thing was the polarization calibrator that we are not going to do in this tutorial. So it's better to visualize also, no? You see the next thing on the menu. Also, let's show you these things. So why we need calibration? There are 3 calibration that we are going to do. That is gain calibration, to correct with the time. There's a delay calibration, that there's a pointing thing, right? Delay I told you about, and there's a phase calibrations. So the band pass calibration. So with the frequency, you want to correct the amplitude and phase with the frequency also, right? So let's plot these things to get to you can plot of your own also. Let's do it, no problem. I'll do it fast, okay, this time. It's better when I can see you also, so you could have asked questions and all. So I'll do for only the phase calibrator field with the, let's go into the UV space. The UV space was the parallel thing with the rays I told you about, right? UV distance, okay, amplitude data for the phase. You see right here, right? So the points for a point source, it is like this, okay? The amplitude distribution is relatively constant as a function of UV distance or baseline length. So the maximum baseline length was 1 kilometer that you can see, right? So there are you see there are more gaps in the here and very small gaps here. So it is the gap of the there are much more smaller baselines. Remember, if you see the plot, CASA, yeah, yes, that we made, right? So the smaller baseline, I think EO8, EO15, EO8, EO22, EO8, 16. So there are many small baselines, then bigger baselines. So bigger baselines are less, right? EO18 to EO3. So there are limited number of maximum baselines and minimum small baselines are much more. Okay. Let's go back and do for the phase calibration. Oh, phase calibration. You see there is again amplitude, you can see this varying, but it's really more concentrated here. So it's a point source. And let's see our target. How does that look like? So this kind of thing show you a resolved structure. Okay, such a visibility indicates a highly resolved structure. If you want to know more, just read the manual here. You can it's very easy to know. Okay. So they have also plotted here this thing. So the only two polarization on all the pointings. I am just plotting here is one pointing, and you can see here this also. So let's plot. I want to give you EA again. We go they have plotted for what? EA01 to EA21. I am plotting for EA20. No problem, right? Baseline. On axis I am changing to what? X-axis to be channel, and Y-axis, let's say amplitude. What is like that? Yes. Iteration over baseline. Yes. Channel amplitude. Is and let's average over time. So I'm putting 1 is A6. You can give anything you want. See, I'm doing some. Oh, I was doing for the target. Shit. Let's go back to the original thing we want to plot. Let's not do in time also. Okay, look this phase up. So this was for one polarization and this. So you see there is starting from -20, -40 and going there in channel. It's changing, so that's why you need correction in channel phase frequency also, right? So you need to, and this you see there are different slopes, right? Let's go to another baseline. So this EA02 and EA20, so they are different slope, but they are linear, right? So you have to correct for those for each antenna, each baseline, right? That's why we do the calibration thing. Okay. And there are many more tasks that you can run to flag the data. Okay, how much recording I have done? Let's see. Oh, it's already been 1 hour. Okay, I'll do it fast now. So you know how to handle CASA now. like not fully, but now you get like hands see how to see what you are running. You can plot from here also. So there is a visibility, right? True visibility that you don't see. There's also only the observed visibility you see, and multiply by a certain number of factors, that is this theta I and theta j. So theta I for antenna number I and theta j is for antenna number some other antenna j, and there is a visibility which is multiplied by the g factor, which is the amplitude gain correction that you want to do, and b are the band pass complex thing in frequency and time, so you need to correct for those also. The Bij is the if you see if there is a that you have measured your like distance, the baseline distance, not more accurately, that there is a like error in 1 meter, let's say 1 meter is greater, like 1 centimeter people there is a, then in the calibration the 1 centimeter will give you errors, right? So you have to correct for those also. So what like GMRT antenna doesn't move, but the VLA antenna moves, so it's and to in D configuration to A configuration, so 1 kilometer baseline to 50 kilometer baseline. So they keep on changing every 3 months. So when they point it when they put it back, there is a chance that there is a error in the where they have put it, like 1 centimeter, 1 millimeter, whatever. So you have to correct for those also. Okay. GMRT doesn't need that, so we do that by using a task called GenCal, so it's general calibration. Okay. TGET. Now let's say I put the TGET, so I haven't run that task before, right? So TGET, sorry, no task has been saved, ran before. So INP, it will use this visibility again. We'll put the visibility cal table. Okay. Let's give the same name, otherwise you will also get confused when you okay. Yes, Control C, Control V, cal type and position. Yeah, okay. And let's go. In the CASA logger you can always see. Okay. Okay, you can see there is a in meter there is an offset. This thing's in meter. Okay. So there is a, so it created a file. These are folder, actually what we call them files. Okay, so it's a cal table that has been built which have this pointing errors, this antenna position error. Okay, so when you do the calibration you put this file as a input to the more calibration that you want to do. Okay, so I already told you that you have to know the flux density of your calibrator, right? So we'll set the frequency of our calibrator with the how much flux density it does have actually, okay, on the particular frequency. Okay, so this is a task called set Jansky. So just Jansky, I think it's a unit of flux density, right? Spectral flux density. So it is like 10⁻⁻26 watt per meter square per hertz. I think ma'am or Abrup sir have already told you about this. Okay. So it's how to do is provide a flux density to your amplitude calibrator, which will later transfer to the flux density scaling to the phase calibrator and later to the target also. So you will know the true flux density of your target. So it's to do that, I'm doing it. I don't want to disturb this. Let's do it fast. List of list stops, if you do, you will get the model, which flux calibrator it already had been saved. Okay, so let's do our thing. So list stops we don't do. Let's check field. So they have given this. You already know, right? Field. You can give field ID also instead of name also. Okay. So INP. So standard. There are many standard. Perle Butler 2017. This is the latest one. Okay. You can also get the model number. Okay. So there. This is in C band. That's why it's there. INP. User scratch false. Everything is changed. What you will see in the CASA logger, right? You see there is the source at C band. It's 7.6686 Jansky. Okay, which is a very good bright source. Okay, you can see here also. Let's do the calibration. So there's a task that you can do on all the calibrators just to see if there is any bad antenna that is left. Okay, so we'll do this on the gain calibration. So how do we do calibration is gain cal. Okay, get. Let's not do get. I mean, I will do that. INP gain cal will take the parameters from here. So let's do cal table. So 3C391. You can give any name. You don't have to give from here only, right? Then just Z0. We are doing the gain calibration and on all the calibrators. Okay. Let's see this. INP and previous tables that you have built, you can give here as an input, right? So we build antenna positions thing. Okay. Field ID you can give, right? 0 and 1. We remove the 9th, which we don't need for polarization calibration. Cal mode is already cal mode. Cal mode is given as a phase calibrator as P, amplitude as A. Okay, solent. How much data you want to average? So for integration time. Okay, so it will just take calibration at each time step it will do, and you can give SPW how many channels you want to use for the calibration. So you know when I plotted the amplitude versus the channel, you saw that the channels in between were good and the channels at the end were bad, right? So I give it's better to take the channels from in between to do the calibration. Okay, so let's they have chosen 27 to 36. You can choose whatever you want. I'm choosing the same thing. You can choose 20 to 40. Okay, they are also good. And gain type is K for delay calibration that we will do in a second, and minimum SNR. Okay, minimum of number of baseline you can give is 4. Minimum SNR is 3. So what that does mean is, if the gain calibration is done per antenna, okay, antenna wise calibration is done. So for each antenna it will do the calibration and give you the calibration parameters. But for each baseline you have like a if there are 26 antennas, so you have 26 baseline for each antenna, right? So the minimum number of baseline that are required to do the calibration, it's given 4. So if at particular time step you don't have 4 baseline, right, so it will not do the calibration, because which will be not be good, right? And means minimum SNR you can give signal to noise ratio. Okay, so they have given huge, because there is good data also at a very high frequencies, 4.5 gigahertz data. If you have done into the low frequency, then minimum the SNR would be very less. Okay, the signal to noise ratio is very less, like people use it around 1. Okay, so if you give a high SNR, then more of your data will be flagged. Okay, so they have given 4, and let's use 4 only. Otherwise, some of the result you will see will be different, and you see Sarvesh is doing something wrong. Okay, so let's go with them only. So if they, oh, I didn't give field ID. I did. So at each, there is this is a found no unflagged data, right? So at each timestamp, there are some, we did the quack thing, right? So it flag at that time, it didn't find anything, right? So the data was flagged, so it didn't found anything. That's why it's giving this. So out of 248, 212 are the good ones. So in C, you can see what is the table that is printed, right? So G3C391 G0 all file, new folder has been created. You can see this file as a plot cal also in this plot ms. So in the later version of cover, this version you can see as a plot ms. So I will give you into plot cal. Okay, so x-axis is cal table, x-axis it's time, y-axis to be phase, and we did the phase calculation on this data. Field we don't want to play, because already we've taken SPW, we don't want to play. Fig file, we don't want to save any pictures. Okay, iteration ever, we want to see antenna wise solution, right? So antenna wise and plot range, color axis. So we'll see the color for each polarization RR and L. Let's go. So A1 you get a very good antenna, right? Very good face. This is also good. You see there's a here some point, here some point, but it is good. It is not bad. If you if you think it is bad, it is not, because after it is into minus 180 to minus 180 to 180 plus 180, right? So it should have gone to how much, 181 or something. So it can't go, it went back to minus thing. Okay, so it's only from 0 to 360. That's why these are the phase jump. Okay, these are also good, right? So in you can see that in antenna number AO5, you see there are some phase jump, like around 80 it is here and 150. So there are phase jump in this, right? So you can flag these individually. You can flag it here, mark region and flag. But this is bad, right? You don't know this line is good or this line is good, right? So you should flag the whole antenna. In other antennas you see there is a certain thing, certain like pattern you can see, but in that antenna you so there is a phase jump. Okay. You can just cross it here. If you want to put just seen all the antennas. Okay. So we found that antenna A5 was not good. So we can flag like we did it before, like flag INP or TGET flag INP again. Visibility mode is manual, right? And you give the antenna. Antenna name is EA05. Action apply. Okay. Now let's see how much data we have flagged. Okay. Summary INP. 29.7% of the data we have applied. Okay. With 3 antennas we have applied and quack we have done. Okay. So let's go for the first calibration we want to do. Before the bandpass calibration we have to do for frequency. We want to correct with the frequency, right? So first do the time and delay. So otherwise if you don't do time and delay first, then they will create more calibration problems before the frequency. Okay, so you have to correct for first time then frequency. Okay, the delay is also time delays, right? There is a time delay, so you have to correct for that also. So just we'll do for the time thing. Okay, let's do it fast. Okay, we'll do on the T-get gain cal INT. Field ID is 1. You only do on the phase. Flux calibrator will transfer back to the transfer it on the phase calibrator and to the target. Cal table. When we target to in the phase calibrator, we will transfer from phase calibrator to target. So it would automatically indirectly getting like transferred to with the flux calibrator only. Okay. Which gain calibration. Let's see, they given the same name they have given. Okay. You have to choose one reference antenna also. Okay. So one reference antenna. So you should choose your reference antenna like this. In that the amplitude is much constant in time. Okay. So you should choose from the in the between. Let's go back to the pattern antenna thing that we have done. Right. So you must choose from the nearest. Okay. Okay. So it is like equidistant from every antenna. So but you shouldn't choose the middle one because it will create shadow effect in the UV plane. Okay. So you see that every UV plane that I have talked to you about, right, in the tutorial in this slides, right? This plane. So there is some shadow effect in the between. There is a like white and empty space. So you shouldn't choose from bilkul on the center. You should always choose from the middle and but not the middle bilkul middle wala. Okay. In this they have chosen, I think, EA21, so we can choose that also. What they have chosen, EA21. Okay, let's go and choose this as a reference antenna. Solent. What is solent? Solent to be integration time. You can take solent to be more than SNR is 5.0 IMP. So you must check before running now. Okay, visibility I've given, cal table, SPW, integration time, the reference antenna I've given, minimum baseline is 4 signal noise, gain type is G for time. Okay. And we'll do for delay is to be K, cal mode is P, and the prior information we want to give as a gain table this. Okay. Just go and just go. Let's see what we have done. Plot cal. Okay. And IMP cal. X-axis time, phase, cal table is this, INP, time and phase, antenna, iteration antenna, go. Which field ID I have given? Oh shit, I give different field ID. Sorry. RF, SRF, get gain calibrator. I'm so sorry, I've done it wrong. Field ID it should be 0 plus for flux calibrator INP. That's why we should remember what we are doing, right? So INP plot cal. This plot can time phase is SP2 we don't want to give. Right. See. So these are very good, right? Very good. In the real data, there's very sometimes you don't see. In my data set, you can't see this much good data. It's a very good data at a very high frequency. That is why. So now we'll go back and do the delay calibration. Okay. So tget again, tget gain cal, INP cal table. Okay. Now I will change into K. So it's different file name. Okay. Just give you what you want to give. Okay. Field ID is this, reference ID is same. Now SPW I want to give over the whole data set. From I told you like 5 from the starting and 5 from the end were bad. Right? So don't give those, otherwise you will get the bad solutions also. Gain type. Now gain type I want to do the delay calibration. Solid. I'll take the whole scan and then I do INP. Also I want to combine my holes, the both scans, so otherwise you will get a solution with each scan also. So combine the scan and consider as a one scan. Okay. So for each antenna, for one polarization you will get 1 point for each antenna. Right. Reference antenna should be same. You shouldn't change now. Okay. And gain table. Now prior gain tables are 2. First was this. Now there's one more table that you have built, right? So give that also. Let's go. It's good practice to check, so you get once, right? Scan wise and time. So let's plot it. Tget plot cal INP. So cal table was KO. X-axis you want to see for each antenna. Now y-axis is delay. Now plot range you don't want to give. Okay. Field ID changed to INP antenna. Don't want to give iteration also, right? Because I have already given access to the antenna. You see, there's only nanosecond delay in -4 to 4. This is a very good delay. If you see some point that is like outside this, like in microsecond, then that was a bad data, and you should flag as mark region. Go to mark and just flag it. I'm not flagging it. So I'm unmarking it. Now we'll do the band pass calibration, which is the calibration for frequency. Okay. So T get band pass, IMP. You see the cal table now. You see band pass for B0. Okay, same thing. Field ID is flux calibrator. Reference antenna should be same. SPW you can give the whole also, and or you can give the selected channels. There is no matter. Okay, and people usually delete those 5 channels from the starting, and they haven't deleted it, so I'm not deleting it just for the sake, but you can delete it if you want, and you can see the changes in the tables. Okay, solid to be made again, right? And there's one more table now, right? So gain table will be get updated every time you make a new table, right? So this 3C now I'll give the delay one also. Check. Always take a range check. Okay. Still some. I don't want to delete anything. Giving minimum SNR to get like good solution and less flag point. Let's see. There are 28 solutions. So at one point it didn't find anything. It chose a different antenna, but the reference antenna that we have given, it didn't found at particular time. It didn't find any good solution, so it took a different alternate antenna at E11. Okay. You see, there's this some channels are to be flagged. Okay. Okay, that is not good. I have again I have done something. Sorry, man. The field ID I didn't keep, so it just taken solution from the. It's good practice to check back again. T get gain cal. But there I have given some. Field ID was given in the gain cal, so there was no mistake in the delay calibration, only the bandpass calibration I have done something wrong. So let's get back and change it. Okay. So now the field ID I should give. Sorry, field ID. I removed it. Okay. I'm doing fast, that's why I'm doing something wrong. SPW. Okay, go. Now there's one solution. I also, because there were 28 scans, that's why I took all. Find the bandpass solution for each scan. Okay. So we'll see what we have done. So tcat plot cal. Cal table to be this bandpass. Now we have done. X-axis should be channel, right? Channel. And y-axis to be phase. Plot range we can give it. And iteration to be antenna. So, this is a good solution. Let's see it. You see, whenever the phase solutions I've shown you in plot MS, you see the phase jump region, right, in like -180. Now you have corrected for delay. That's why all came near 0. Okay. Okay. For each antenna, you can see If you find any for a particular channel, you see the solution to be here, just flag it. Okay. You see there are 64 channels, but every time it plotting 128. Why? Because there were two polarization also. Okay. So these were the phase one. You can also check for the, if you change the y axis to be amplitude. So let's go. So you see for the amplitude. Oh, sorry. Now you don't have to give plot range, right? Because that will be stupid. See again the 5 solution. Which were bad. Right? That's why people delete this data. You can also delete if you want. You can check whatever you want to check. Now let's make the final gains solution, gain calibration. So we have made the time gain solution and then the band pass. Now we put all the information that we have collected and put back into go and find the gain solution again. Okay. Get gain cal. Okay. Calculation to be this. It was G0 before. Now it is G1. Field ID again. We have already selected SPW. Already selected solent is infinite. Before it was int. Now we'll just get into the infinite. We'll take only one solution per solent. Okay. Referent antenna, same gain type to be G. Cal mode. We'll now do both the. Before we did for the only the phase solution, we'll now do for the amplitude also. Amplitude and phase both. Gain table. Okay. So G0 we don't want to give, right? Because we are making G1 already. So what should we give? We should give our band pass one. So it's like a kind of interpolation. It's linear if you don't give anything. Otherwise, so for band pass we are giving nearest. So if there is a particular band pass, one channel is flagged for one antenna, so it will not find the solution for that antenna. It will not find the solution for that channel and that antenna, right? So we'll give the nearest one. Just take the nearest and do that. So by doing that, this less data it will be flagged. Okay. You want to flag all the bad data that you can find, but you don't want to. You want to also minimize the flagging. Otherwise, there is a over flagging. You should always avoid over flagging. So these all will find go. Let's check it again if I'm doing something wrong. Minimum SNR should be less, right? Because we have give solent to be infinite. So 5 SNR should be very hard to find. Okay. So let's go. You want to do the same thing on the phase calibrator also, right? So but we don't want to make new file. We can just append the solution into this in this G1 only. So there is a command append root. Append is you just put it in the table form. There is a in the Excel sheet you have 100 rows. Now you are just appending 101. Okay, just like that. Okay. So all the parameters you can see there is a same, right? So INP, you see sol norm is false. Okay, it is good. Linear. I didn't give linear, right? I gave only the nearest one. So it automatically took, because I told you the default is linear. Just go and you can check if you want. Do you want to check? Let's check. Okay, plot care. How much time do I left? Table again. G1. X-axis to be time, right? Amplitude, antenna iteration. So you see what is happening, or you don't? I've done again something. Then I didn't change it into combined scan to what I was doing. Just remove the file, okay? Now tget GMRT G1 field ID to be 0 combines nothing. Okay. 0, everything is safe. Okay, just go. Now field ID should be 1 and let's go again. Tget plot error. T guard लिख दिया मैंने, sorry. Time amplitude 0. Now we got for each scan, okay? The final solutions. This for amplitude is very near. You can see it is not bad. If you think it's bad, let's check for phase. Okay, y-axis. If we found any phase jump, we can remove it now. Okay, these are safe. I didn't give plot range that why there is a spread is minus 30 to 40. Yeah, let's give the plot range also. Oh, it's not that bad. Let me show you one thing. Again, let's go for the reference antenna EA21. So these are overplot. So what reference antenna did is you just like forcefully you did this thing, put that antenna phase to be 0 and calculated all other antenna phases. Okay. You see there is a linear, which is okay. So there was some came because there was some problem during the delay calibration, but that was not like totally here to here. If it was like that, you should have flagged that antenna also. Now let's see. Now let's transfer the gain solution to my scale. If you want to see what is the output of the scale that you have chosen, Otherwise you should can run this part only. You don't have to save this. So that's why flux, and let's do no this way. T get flux cal I sorry flux cal sorry visibility cal table you already know. Okay, flux table reference from to which reference is 0 ID field and transfer to 1. Okay, only one input, that why it didn't show any error. It is showing red. What is default? Display should be false. That's why I was like T get flux table reference transfer B. Now what? Incremental. Okay. Or you can do it. You can run it again. My scale is equals to flux scale. Now you can see what is my scale. Okay, it already exits. You can see here what is happened, right? So at frequency this, so the flux calibrator for the flux calibrator 2.2 is the Jansky source series. Okay, there is also 2.2, something like that. Now we'll apply the solution to our target as well as the flux calibrator and the phase calibrator. We didn't apply, so there was nothing changed in the original MS file. Now it will get changed. Okay, so T get apply cal. So it's a field ID. Now I'll change into flux. First we apply into the flux calibrator only, and gain table, which is antenna position, delay, band pass, and the new that we have created, right? What we have created is the flux scale, antenna position, flux scale, delay, and band pass. And remember, in the flux scale there are two IDs, field IDs. So now you have to give the field ID also. Okay, so for the first one you don't have any field ID, but for the second one you have. If you are applying for the flux calibrator, then you should take the field ID as 0 only. Okay, because you can't apply the phase calibrator solution to a flux calibrator solution, right? So it should be change 0, and in the delay you don't have any field, only one field is there, so it will automatically take that as a default, right? Interp, again same concept. To give 4 because there are 4 tables that you have given, this and this to be rest. This is putting weight. You don't want weight for your. You can detail study it when you do your thing. I should check. No, I've done so many mistakes. I don't want to mistake it again. So the visibility is same. Field is I'm applying to the flux calibrator, SPW, all SPW. Time range, select data. I don't want to. So gain type, gain table I have given the 4 table, antenna position, flux scale, delay and band pass. Gain field I have chosen for the flux scale only, second. Let's go. Let's go, right? Now it will create apply backup 1. Apply cal 1. And how much data is flagged? So before it didn't flag any data, you can see. The data was very good. Otherwise, what would happen is by applying the antenna position, maybe one antenna was bad and positions were antenna position doesn't flag. Let's say some channels were flagged. Okay, so it could have flagged here some data. Okay, here some data. Here some data. Maybe in the target you will see, not here. We'll see. Yes, flux calibrator was good. Now you apply in the phase calibrator. Field 1, but gain field also have to change, right? Same antenna position, flux scale, field ID is changed, right? Same nearest. Everything is same. Okay, now go. Here also I didn't flag anything. So very smooth data. Okay. Okay. Now apply to your target, which is field number 2. If you are mistaken, just do the list stops again to check. Okay. So its target is field ID 0. Is second, so just keep it, apply care, INP, field ID I should change to 2, but you don't have gain solutions for the target, right? So that's why we have taken phase calibrator, right? So we should apply for the phase calibrator. So gain field we don't want to change, okay? Everything is same, only enter. So nearest change to linear, or you don't want to give, then don't give, because it will automatically take linear as a default parameter, right? Again, let's go. Now you can see there's some flagging was done. Okay. In the band pass didn't flag anything, but when they applied the final gain solution, around 3 plus 4, like 7 to 8% data was more flagged. Okay, so that was the bad data. Now see the final solutions. Okay, so before let's go and check. I will tell you. I'll just get that. Not in this. Go. Sorry to go give you blank. We'll check in the MS file. Field ID. Let's go for 0. x-axis time, y-axis to be amplitude, and column data is corrected. If the data column is there, then you will see the whole when you apply, there is a new table that is being created inside your MS folder. Okay, so let's go and check. You see, before the spread, remember it was a spread from 0 to 0.3. Now it's changed to around 7.5. What is changed? Let me tell you. I don't. If you were there, I would have asked you what. So it is because of the set Jansky, right? You change the scale, so you multiply the. You said it is not 0.3 or 0.2. It is 7.6, 7.5. That's the Jansky. The true flux density of that source. Okay. So now the spread is very less in percentage, if you see. Okay. When I shown you amplitude, phase also, it was like minus 180 to 180. Now let's see what is there. Now it's minus 20. It's between minus 10 and 10. This is very good. Okay. So there are some unleft thing also there. So you can like narrow it down and flag if you want. So just plot it by channel wise, and you can see there are some. You don't see anything. So you can see here also the spread is around so this is how we do. This is how we like narrow it down. If there is some problem. So let's narrow it down. Let's see if there is this problem is every antenna or for a particular antenna. Let's change. You can like narrow it down. Yeah, you can see there is more spread here. So EA18 you can narrow it down, and EA23 also there. Right. So channel is more like same time, same none, and then check. So this is in this scan there is a problem. First like choose the scan itself. One scan. Oh, first scan was flat. So 2. You see there is a. Now you go to antenna again. Okay. So we have both polarization also. You can like narrow it down that way also. None. Let's go back to back. Let's only give one polarization. RR. Okay. RR is bad. LL. LL has the same thing. वैसे इतना बुरा भी नहीं है. -20 to 20 है. Then if you have irritation, just flag the whole thing. Like select here, mark here, and just flag this way also. You can flag. Let's flag it. Okay. So this is flag. Okay. No problem. Oh, I did for LL only. So RR also. Let's do it. No problem. Now go back. Let's do phase in the y-axis. Let's put amplitude in x-axis. Phase, amplitude and phase. What we get is a circle, nearly a circle. It's good. It's a very good data. Yeah, very good data. You will get a very good image. Okay, you can go and check for again. Sorry, I closed it. You can check like go corrected, amplitude corrected for our Let's check for our phase calculator. Which is also very good, minus 20 to 20, and you don't see a circle because there are some point here, so you can just select and clip them. We call this as a clipping. Okay, it's flat and let us put circle. Okay. You can also clip from here also. Again, now you get a good circle, which is around 2 Jansky source, right? 2.2, we have checked 2.2.6 around, which is around here. So if I average over all the channels, let's also average for in time also. So what we get a more smaller circle. Minus 3 to 3, which is very good considering minus 180 to 180. Right, you can see for antenna per baseline, you can like all the you don't want to do in time, only channels. Okay, in time don't do 3 channels. This is very good. And you see there is a 2.2, before it was something else and now it's 2.5. Just quit it. You can plot this, okay, and check what you are getting. So now it's target. Let's split the target again. Okay, T gets split. As we want to do imaging, right? So this output visibility is target. Don't forget .ms, okay? Otherwise it won't read. Oh, output is and data column. Corrected. Okay. And field ID. Field ID is, for our target is 2 INP. I'm not giving correlation as here because I have already given only RR and there were 4, right? That's why. Let's go. So there is a new, you can see there is a target file now. Okay. Now we'll do the imaging on the target itself. Okay. We'll take time. You can see some parameters I'll make you see, but it will not look like this because I have only done for one pointing. Okay, they have done for the whole thing. Okay, so let's stop it now because if you get time, I will just do these parameters and you will get it. Okay. I'll tell you about some parameter of this. So you have to give a cell size, like pixel size. Okay, so it's like 2.5 arc second. You can calculate it at a given frequency, right? And from the resolution, like lambda by d. Okay, you can calculate it from there. Or what is the image size? So 480 by 480 pixels. Okay, and what is the threshold? So the noise level that you want to like reach. So if this source is around 1 Jansky, So 1 millijoules is very like a good the noise. This the blue one is here, all the noise, and this is your target. Okay, this is the remnant that you are getting, the super remnant. And later, how many iterations you want to give? Okay, there are like you will read this and you will get. So greater is mosaic because there was 7 pointings. Remember, so in this only 1 pointing. So I think if sir was here, he would have said you the same thing. Just repeat this thing. I can do for the calibrator. Okay. Let's do for the calibrator, and you will see they have not done for the calibrator. So we will see a point source, okay, because we have taken that to be a point source. Let's make it for that. Okay, so T gets split again. I and P. It's already been too late. Sorry, I'm very slow in explaining stuff. I think output visibility. It changes to flux calibrator, right? MS. IMP, field ID 0, go. Okay, it's split it. So now we have LS minus LHRT G. This is a flux calibrator, right? Now let's do T clean. T get as default. Okay, I'm doing something wrong. So I don't want to do it now. T get T clean. Visibility is now your flux calibrator. So this flux.ms IMP. What is the image name you want to give it, right? Image name. Data column is data, right? Now the data column, corrected data column in the new folder, it is data column, right? Image name. Target 1. Let's give target underscore 1 as a image name. Okay. You don't have to give field ID because it's already one field. Right? IM size. Let's give what do you want to give? 240. So, or we should give 256, right? Multiple of 2. You should always think about that. Like 128, 256, 512. Okay, like that. And cell size. Again, we will give the same 2.5 second. Okay, cell size. These are certain parameters for this only, na? So I'm not giving it here, but let's read for threshold and knitter. I should give knitter, right? If you give knitter to be 0, that it's a dirty image. I've shown you in the slide already. You can go back and check. So I'm giving knitter to be like 10,000 or 5,000. Only 1,000 can do the stuff right now, but let's give knitter and threshold. Okay, threshold. How much you want to give? It's a 7 Jansky source. I think sir have already told you about the class sensitivity. People usually calculate from there. There's a formula sensitivity you can calculate from the cycle meter. Then projection is going to how one is good. Okay. Waiting. Okay. In this same model is if you want to do the self calibration. Okay. You can check it from here. I'm not gonna do it here. It's, yeah. So cleaning, self calibration, like you have done the imaging first, then then find the gain solution on that image. So it will take the model data column already and make you the gain solution. Then apply this into the same data and make a new image. Okay, and you do this for like 3 to 5 times and you will see much better image. They have not provided. I think you should do it if you are doing one. Okay, so let's go and check what image will get. Okay. So it will take some time because cleaning is I don't know, it's a very small data set. It will not take much of time. So you will see it's like running fast and fast, doing the iterations. Number of iteration I have given 5000. It's already been 30. It will like increase it as soon as so there are two parameters that we have given, number of cycles and the threshold. So number of iteration I have given 5000. So after 5000, whatever it is, it will show you the image or it will reach the threshold. So 2 point it is like stop. So all the 5000 iterations has been done and it didn't reach the threshold. I think I've given a huge threshold. I should have given to like 5 milligens or something. Let's see. So it's a viewer. Okay, I did on the flux calibrator, right? But I have given the image name to be target. I'm so sorry. I don't do it. Check it. I have flux and target. So it's like a. I will not do it again. You can see that there is a point source, right? So there is the synthesized beam, the PSF. Okay. So you see here what is the noise level also. So this is the noise. You see this is noise. So there is a pattern, right? SSA pattern RF. So this can be, but it's not coming -3. This is a good point source. -2 you won't see it. So it's only the least scales you are seeing, right? -5, or you can go back and change to -7 also. Oh, this maximum is -7. I didn't know this. You see, the scale is the image size is getting down, synthesized beam is smaller. It's just because of the scale parameters, nothing more. So just go for 0 for the original thing. You see, you can zoom into the synthesized beam. I think let's stop it here. And now I should say, if you have any questions, then you can mail me or sir, right? What I have done, I can send you these files, no problem. I can send it, but please download it by Monday or next Monday. After that I'll delete it because it will take some space into my Dropbox. Okay, I will like keep all this. This you already have, so I will delete it right now. Okay, I'll delete it. So exit. Acha, there's one thing. So this CASA logger is there. Okay. Now if I exit it, okay. Now there is a CASA logger here. You can see here, right? So gedit CASA. So what the task you have run is are saved here. Okay. Every time you run, it is here. So don't worry. You can see. You don't have to run it again and see what I have done. You can see here and see what I have done with my data. Okay. Already. So this is a huge file. It is around around 6,000 lines. Okay, so you get a better. Make a target image and show it to sir, I think. Okay, bye guys. Hope you learn something new.